Hey guys, welcome to today's class, and today we are going to try to cover the VSEPR theory. But before I get started, what is the use of this all? Now, we often know how C binds with H, right? We have talked about the covalent and the ionic bonding in the past videos if you need to check that. But we know a lot of reactions depend on the shape of molecules. Specifically in biology, a lot of it depends upon the shape, right? The enzymes and the substrate reaction. Now, how exactly the shape and the molecules, the shape of the molecules is determined, right? How are the electrons arranged? How are the atoms arranged in a molecule? That is what is the stuff of this whole video. Try to understand what this video is all about. This is all about understanding the molecular geometry. That means what is the shape of the molecule. Now, as with everything, theories evolve over time, right? So we know atoms react to form molecules, covalent, ionic, which is covered, but where are the electrons in the molecules? Somehow, the VSEPR theory, which we are about to cover, will give the answer to that. What shape of these molecules, what shape do these take? That also can be answered using the VSEPR theory. Now, the distribution of electrons. We will talk about polarity of the bonds and hence of the molecule, and how does this affect the shape of the molecules. But VSEPR theory alone cannot explain the entire process of bonding. The process of bonding is better explained by another theory that is called as the valence bond theory. This is being covered in another video. Check out the suggested link in the description as well. So, without further delay, let's get started on the VSEPR theory. Now, the theory is, if you see, pretty simple. Valence shell, electron pair, repulsion. Now, I sort of am a fan of how things make sense when you read them backwards. Repulsion, add-on of electron pairs in valence shell. So this theory basically says that the electron pairs, or better called as electron groups, why I will clarify that in a little while. Electron groups are placed around the central atom, the atom which has the maximum number of other atoms bonded to it, in such a way so that there is a minimum repulsion. So we need to position the electrons around in a manner that we have minimum repulsion possible. Now, let us start doing that, and the first molecule that we'll be covering about is BeCl2. Now, if you remember, Be shows an exception to the octet rule. If you want to check out what is the octet rule or what are the exceptions to the octet rule, the links are down below. Now, so let's talk about Be. So hydrogen, helium, lithium, beryllium, that is 4. Now 4 electronic configuration is 2, 2. That means the valence shell has got 2 electrons. So how do we do this? So first is you have to write the Lewis formula. If you remember the Lewis how to write Lewis formulas, that would be a great help. If you want to check out videos on the same, the links are in the description below. Now, you write the electrons of Be, right? So valence shell has got 2 electrons here, and the chlorine, if you remember, has got 7. The atomic number of chlorine, Be was 4, chlorine is 17, that is 2, 8, 7, right? So these are the lone pair of electrons the chlorine has, right? So this is where the bond is. So we have done the first step, that was writing the Lewis formula. The second step is count the number of electron groups on the central atoms bonded and lone. So this is 1 electron group, this is another second electron group. Now, remember, when we say electron groups, we will not be differentiating between a single, a double, or a triple covalent bond. And we'll be considering the lone pair of electrons as well. Now, beryllium does not have any lone pair of electrons, but if it did, it would have made a difference. And how, we are going to look in the further examples. So, BeCl2, that's the Lewis formula. We have counted the number of electron groups here, total 2. Now, arrange the electron pairs according to the VSEPR theory, that's step number 3. Now, you have to place the electron groups around Be such that there is a minimum repulsion. I hope you remember this, right? So, the best way to do is place them at an angle opposite to each other, 180 degree. So you can simply say that this is the electron must be linearly opposite to each other. So remember, the red step gives you the electronic geometry. That is, what is the distribution of electrons around the central atom, and the blue gives you the atomic geometry. Now, once you know where the electrons are, you can determine where the atoms are, right? So once we know that the electron groups are here, we can position chlorine next to it. So linear is the geometry for BeCl2. The last point that we must discuss is about the polarity. Now, what about polarity? Now, if there is a charge separation between the atoms involved in a bond, obviously the bond is going to be polar. Now, I hope you looked at this tiny piece of information that I presented, the electronegativity. What is electronegativity? It is the power to pull the electron, right? Power to pull the electron groups towards itself. For chlorine, which is a highly electronegative atom, it's 3.16, right? And for again, both the directions, the chlorine is pulling the electron cloud towards itself. So we can say both bonds are polar, but they are in opposite directions. They are polar, but in opposite direction. What does this mean? That means the net dipole moment of this molecule is going to be equal to 0, because the dipoles, they cancel each other, right? So you can see how the geometry is very much linked to the polarity of the molecule in itself. Now let's go to another molecule, to the next problem. Again, we have another BF3. Remember, again, boron also has or is an exception to the octet rule. It only requires 6 electrons in the outermost shell, like beryllium required only 4. You can check the video in the description of the various exceptions to the octet rule. So, write the Lewis formula. So, boron is 5, atomic number 5. That means 2 comma 3. That means you can write 3 electrons are in the outermost shell. F, fluorine, is, well, 9. That gives you again 2, 7. So quickly we'll position the electron of the fluorine. Now remember, that's the first step, the Lewis formula. Second, count the number of electron groups in around the central atom. Oh, we forgot one fluorine here. So we can clearly see that we have one electron group, second and third. So we have 3 electron groups. Now think about a circle. How can you position things so far from each other so that they are at the maximum distance from each other, right? So yes, it makes sense, 120 degrees apart. So the third step was arrange the electron pairs. Now, how would you arrange the electron pairs here? So electron group, center, electron group, and center and electron group. And the angle between them should be 120 degrees. So that is our electronic geometry. The fourth step is determine the arrangement of bonded atoms and lone pairs. Here we have no lone pairs, so you can simply write boron in the center and the three atoms around it, that is fluorine, fluorine and fluorine, and the 120 degrees, and we call this as trigonal planar because they're all essentially in the same plane. Now here what did we not discuss is about the polarity of the bonds and hence of the molecule. Now boron again has an electronegativity of 2.04. On the other hand, fluorine is 3.98. Now again you see this is an extremely polar bond if you ask me. But as we can see, the polar bonds cancel each other and hence overall it is a non-polar molecule. So again we have established time and again how geometry can determine the properties of molecules immensely. Now things are going to get a little bit interesting. Now whenever a molecule or polyatomic ion has no lone pair electrons, now till now we have seen two examples, that is the Be Cl2 and Bf3. Now none of these had any lone pair, no lone pair electrons. So when we do not have any lone pair electrons on the central atom, the molecular geometry is equal to the electronic geometry. Why? Because there is no distortion because of the lone pairs. Now in the next example we are going to see how this is going to vary. So let's get on to it. So the next example we have SO2. Now sulfur is 16 as you know, so that means 2, 8 and 6. So 6 electrons in the valence shell. Oxygen is 8, that means 2, 6 in the valence shell. Now write the Lewis formula. So sulfur is the central atom and we have oxygen, right? So let's quickly prepare 6 right here and 6 in case of sulfur. Now we can quickly see that there is one electron group here, one electron group here, and the third electron group here. Remember, the electron groups right now we are not differentiating single, double or triple bonds, right? An electron group simply means the electron cloud we are talking about, right? So again if you see the number of, if you want to arrange the electron pairs according to VSEPR, we still have the same thing, that the electron, the lone pair of electron, the oxygen and the oxygen, the angle should have been 120 degrees, should have been, this should have been trigonal planar. But the electron pair in the lone pair of electron is bound only by a single piece of a single atom, right? And because it's bound by a single atom, it is more spread and occupies more space. Now when the electron cloud occupies more space, you can expect that it would try to push these two SO bonds, and hence the angle between these are supposed to contract. And in reality, the SO2 molecule, the angle is not 120 degrees, rather it is 119 degrees. And such a molecule, the molecular geometry is not trigonal planar, even though the electronic geometry is still trigonal planar. The atoms are squeezed in together and hence this geometry is called bent or simply angular, right? So it's 119 degrees, that's why. Now that you know the basics of this, I want you to try and cover some of the molecules like CH4, NH3, H2O, SF4 and PCl5. Now these are problems that are going to take you towards higher electron groups, and then you might also even have lone pairs there, and they will definitely give rise to more molecular geometry, even though within the same electronic geometry. We'll discuss these in our next pair of videos. Make sure you are tuned to in that.
We hope you like this video. Press subscribe, thumbs up, and stay geekly.